Hello, and welcome to this snapshot of Dassault Systèmes, the 3D experience company.
Wherever you are, whatever you're doing, Dassault Systèmes is there with you.
Our belief is that the virtual world extends and improves the real world. In life, there are no rehearsals. In the virtual world, we can simulate and evaluate impacts before producing the product itself. Virtual worlds help people imagine differently. This belief translates into a company purpose. Dassault Systèmes provides business and people with 3D experience universes to imagine sustainable innovations capable of harmonizing product, nature, and life. Harmonizing product, nature, and life is how we define sustainable innovation. Let's take our first step on this journey through product, nature, and life with a look at a product, in this case, a car. A car is essentially a product made of many other products assembled together to form the finished article. And what you're looking at here is a car as we would understand it. But what do you think will happen to cars in the future? At a recent Financial Times Future of the Car Summit, there were a few interesting answers to this question. Electric and possibly autonomous vehicles will almost certainly replace the car as we know it today. People won't just go for a drive simply for enjoyment. The car will become a tool or a robot to facilitate travel. But of course, this will have a tremendous impact on the automotive industry as we know it today. There will be an increasing number of automotive companies bringing disruptive innovations to the market. And here is an example. The Chinese car company NIO was only started in 2016 and is now a global company with 3 all-electric family models, a supercar and a Formula E team. The complete engineering team is using our software, the 3D Experience platform, which you can see in the video at the bottom left of the screen. In this video, the design engineer is looking at the assembly of assemblies and then using the built-in tools to perform a clash analysis, which detects interference between components. The minor clash is fixed automatically using the software. So here you can see the designer has isolated the electrical ducting and the front chassis members to which it's connected. He then runs the clash detection analysis, and the software automatically highlights where a clash occurs. He can then use a clipping plane or section to drive through the chassis and see exactly how much the clash is and where it actually occurs. And then use the software automatically to redesign both the chassis and the ducting so that it fits together properly and doesn't overlap. So here are some more electric vehicle startups. They've selected the 3D Experience. All of them are using the 3D Experience platform to get started quickly. They need to concentrate their software solutions on the product they're going to develop, and they want to start with a solution where all the domains can collaborate. The work is focused on the design and simulation challenges to incorporate electrification to their vehicles. In addition, many of them have seen the benefits of the cloud. It's quick and easy to get started, basically in an afternoon, with no infrastructure. You can invite all those you want to collaborate with, all the way through to the supply chain. So what are the design challenges introduced by moving from conventional car design to fully electric? With a conventional combustion engine car, that's petrol or diesel, like you see in the bottom left, engineers have been refining the design and construction over the past 100 years or so, resulting in the fully mature vehicles we see driving our streets today. However, for electric vehicles to compete in this market, we, or you as future engineers, will need to achieve the same level of maturity in just the next 5 years, not only in terms of the vehicle's functionality, but also the overall driving experience. And this will not be a simple task. So here are some of the challenges, mostly around the battery. How do we keep the battery at the correct operating temperature? How do we optimize the battery weight for vehicle range? How do we redesign the vehicle chassis to account for the heavy battery? How will this affect ride and handling? And all of these things have to be worked out and optimized by the design and the simulation engineers. So Dassault Systems has acquired several software companies to help with this investigations. We can use Electromagnetic Software, CST, to look at how the battery will function, like in the top left, and how the electric motor at the wheels will perform, and the bottom. We can use the fluid flow software to examine lubrication of the drive system, at the bottom left, as well as heat throw through the battery itself, in the bottom right. So we can then use the same simulation software tools to improve the design in other areas of the car. The Electromagnetic Software CST Studio Suite is used to optimize the location and design of the radio and mobile communication antennas, and to ensure that the vehicle proximity control will work effectively, as in the top middle video. Now, no one wants to get their hands dirty when they open the car door, so we can use the fluid flow software solutions Xflow and PowerFlow from Xla to look at vehicle soiling due to travelling in wet or muddy conditions. The videos in the bottom left show the difference between simulating this vehicle soiling in the wind tunnel, which is how a physical test would be carried out, compared to the open road, and it's obvious that the wind tunnel test will underpredict this effect. Real-world simulation is also extremely important for vehicle aerodynamics. The fluid flow software can be used to optimize the shape of the car in real-world conditions, as opposed to the wind tunnel test. The video in the bottom right shows that wind tunnel tests can be useful in improving the aerodynamics of the car, but in order to truly have an effect, you need to use real-world conditions. No one drives in a wind tunnel, and there are lots of other things to consider, like crosswinds and turbulence caused by other vehicles and so on. Well, our software solutions allow the designer to take the real-world conditions into account. We can even use the 3D Experience platform software to simulate the factory production line on which our new design of car will be manufactured, including the assembly and spot welding robots. The 3D Experience platform allows the automotive manufacturer to optimize this process all the way from concept to final product. So here you see the robots placing the side panels up to the main chassis member. Then the vehicle moves down the production line, and the next robot puts the roof panel in position. And then we move to the next station, where the spot weld robots will apply the spot welds and join these panels together. The location and movement of all these robots is driven inside the 3D Experience platform, so that when they actually get to the factory production line, they know exactly how it's going to operate. Now, let's look at how our software can be used to help design a smart city as nature. Virtual technologies have been used since many years by many industries in the aerospace and automotive markets. Now it's coming to the cities, and it's really an interesting way to think about the way that the cities will transform and have a better future.
As a compact island state, Singapore faces many challenges as it grows. The government is working to ensure that as this rapidly changing city moves forward, the lives of its citizens continue to improve as well.
Singapore has a vision to be a smart nation. To be a smart nation, it doesn't mean all about technology. It could be about people, it could be about processes, it means about doing things much easier. But technology does play a big role in making the nation, the people, doing things in a more efficient way.
Humidity, temperature, and even noise and light intensity are recorded on devices worn by students. This data is fed back to Virtual Singapore to help build a comprehensive 3D model of the city.
So Virtual Singapore wants to be the platform where we could test different ideas, provide services that make people's life much easier and more efficient.
The tropical climate of Singapore can result in some parts of the city becoming uncomfortably hot. To combat this, urban planners will often consider how the placement of buildings will affect wind flow across the city.
We are modeling and simulating the way wind flow into a town area. When we run the wind flow analysis, we'll be able to see where are the areas that's being blocked, and we can improve the way that we arrange the building types and blocks so that we introduce wind channels so as to enhance thermal comfort. Now, you can't really do that in real life because that means that you build a building and you found that, hey, you don't get much wind here. You can't just demolish it and reposition it. Virtual Singapore allow us to just grab the maps, very detailed forms, and just run the simulations. Virtual Singapore is really a collaborative platform. Other government agencies can also put data, and so with more richer data, it will mean that we are able to plan better. And if we are able to plan better, it means better living standards and lives for our residents.
We decided to work in Dassault system because we came across a 3D experience platform, and it has some features that allows us to expand on it and develop Virtual Singapore. The team works well with Dassault system. Both are very ambitious, can be open to share our ideas, and this trusting relationship is more crucial than technology can afford us.
Besides the urban planners, engineers, people in the business industry, and even the residents themselves would find that Virtual Singapore will be very useful.
Virtual Singapore allows us to experience the city in a way that hasn't been possible until now. With this platform, we are shaping the future. And finally, is it possible to take the software which has been used for years to design and simulate products like cars and aeroplanes and use that software to create a virtual human? So let's look at life. Everyone has a heart. This is a clinical view of Dassault Systèmes' living heart human model, where we've realistically rendered the response of the computational model. We did this to better communicate with project stakeholders who are not familiar with modelling and simulation, some of whom interpreted the engineering view as a cartoon, and because, as rendered, it's actually somewhat easier to perceive subtleties in the heart motion. The model itself was taken from a high-resolution MRI scan of a healthy adult human male. Then we used a gaming company called Zygote Media to take the MRI slices and produce smooth, very detailed surfaces from which our design software CATIA could produce a solid 3D heart model. When you think about it, a heart is basically a pump used to take blood from the lungs full of oxygen to the rest of the body, and then to return the blood with no oxygen from the body back to the lungs, and so on. The bright colours you could see are the electrical impulses from the brain which drive the heart motion. The electrical signal moves through the heart, causing sequential contractions and therefore the pumping motion. And one of these benefits of using a virtual heart is that you can slice through it pain-free to look at what's happening inside. So the Living Heart project, it was a collaborative framework and community. We've now developed the capability to truly design a device to perform properly without the need for animal testing or costly clinical trials. This was a unique project, bringing together leading figures in research, industry and the world of clinicians. And for the first time in a commercial project, involving the regulatory bodies such as the FDA and the NDIC. During the course of 18 months after its inception, a fully working electromechanical model of a human heart was available for validation and application. The project member numbers continue to grow, where we now have hundreds of members actively engaged in using the model across 24 countries. The current enterprise solution is now on the cloud. The mechanical deformation is shown here with structures like coronaries and 4 valves. What you're looking at is the engineering model and the mechanical response to the electrical stimulus. In the engineering model, the material properties of the heart tissue have both a passive, elastic part and an active part, which causes it to contract when subjected to an electrical signal. There are several benefits to using this type of simulation. It reduces the need for animal testing. It enables you to look at each part individually. So, like in the top right here, we can remove the ventricles, for example, and just look at the atria and the coronary arteries. And then, like in the bottom right, we can concentrate on just one part, for example, the mitral valve. And if this has failed, we can look at the best surgical procedures to help the clinician make important decisions. So what can now be done? Members of the project have already used the heart model to virtually test a full range of cardiovascular products, study heart disease, or novel treatments with the unique ability to know and understand what is happening inside the heart, the electrical system, the tissue mechanics, and the blood flow. This is a profound step forward. The ability to assess device function and behavior inside the heart then opens the door for a variety of benefits. We're not yet at the point where we're doing virtual clinical trials, but we're starting to make some good progress towards making that feasible. So, like in the case of the stents in the middle here, you can imagine that we can use a virtual model of the actual patient's heart and deploy the correct sized and designed stent in the correct location to work best for that patient. Pacemaker leads is another example. I didn't understand or didn't realize that pacemaker leads, once they're inserted, stay inside the heart even if they fail. So we can now use virtual design and testing to make sure that the pacemaker lead will last for the amount of life that it's supposed to last. I hope you found this presentation interesting, and if you would like more information on anything we've shown here, please visit our website. Thank you for your time.